Have you ever stopped to think about how these massive online systems we use every single day actually work? We're talking about thousands upon thousands of computers all trying to work together in perfect harmony. I mean, it sounds like a recipe for absolute total chaos. So the big question is, how do the engineers behind these giant systems keep that chaos from taking over? And really, this is the fundamental question. When you're building something like Kafka or Hadoop or countless other big data systems, you're not just dealing with one computer. You're dealing with a whole fleet of servers that have to agree on things, share work, and somehow handle failures without skipping a beat. So how do they pull it off? How do they avoid tripping over each other and bringing the whole thing crashing down?
So here's the deal. The number one challenge is coordination. It's just plain hard. When you've got hundreds, maybe thousands of machines, all trying to act like one single coherent system, problems are just going to happen. And we're not talking about simple bugs in the code. We're talking about the fundamental challenges of distributed computing. Now, this slide really gets to the heart of it. Let's break down that chaos. First, all these computers have to agree on some basic facts, like who's the leader right now. Super important. They also need a solid plan for when a server just dies, because it will. And then you have to avoid these nightmare split brain scenarios. That's where the network breaks, and you suddenly have two groups of servers that both think they're in charge. Yikes. And on top of all that, everyone needs to be working from the same sheet of music, one single source of truth for all their configuration. If you mess up any one of these, the whole system can just fall apart. So how in the world do you solve this massive coordination problem? Well, you do what anyone would do. You bring in a manager. Or, in the world of distributed systems, you bring in a traffic controller. And that's where we meet our hero for today, ZooKeeper. At its core, ZooKeeper is this super reliable central service that other big systems can lean on for all that messy coordination stuff. Now, it's really important to get this. It is not a database for your normal application data. It's a specialized service just for the metadata of your distributed system. All those small but absolutely critical pieces of information that keep everything running smoothly. And honestly, this air traffic controller analogy is the perfect way to think about it. Imagine a busy airport. ZooKeeper is the control tower. It doesn't fly the planes itself, but it tells every single plane when to take off, where to land, and most importantly, how to avoid crashing into each other. Your application servers? Those are the airplanes. The shared runways and gates? Those are your shared resources, like files or databases. And the flight plan for the entire airport? That's your system's configuration. ZooKeeper is the one making sure every plane knows exactly what it's supposed to be doing. Okay, so if ZooKeeper is the control tower, how is it actually built? I mean, how does it manage to be so reliable that these huge mission-critical systems bet their entire operation on it? Let's take a look inside. All right, but wait a second. This is the big, obvious question, right? If you set up one central controller for everything, haven't you just created a massive single point of failure? I mean, if the air traffic control tower goes down, the whole airport shuts down. So how does ZooKeeper get around this huge, fatal flaw?
Well, the answer is actually simple, and it's really elegant. ZooKeeper itself is a distributed system. It doesn't just run on one server waiting to fail. It runs as a small, super robust cluster of servers called an ensemble. Basically, it practices what it preaches. And here's a really cool little detail about that ensemble. It always has an odd number of servers, 3 or 5 or 7. And you might be wondering why. Well, it's to avoid ties. It's just like a committee vote. To make a decision, you need a clear majority. With 3 servers, you need at least 2 to agree. With 5, you need 3. You can never have a situation where it's a 50-50 split. This little mathematical trick is absolutely critical for making clean, undisputed decisions. No maybes, just a clear yes or no. Okay, so let's break down how this all fits together. First, you've got the ensemble, that cluster of ZooKeeper servers. Inside that cluster, one server gets elected as the leader, and all the others are followers. Then you have your applications, things like Kafka, which are the clients that connect to the ensemble. The data itself, it's stored in a tree structure, kind of like a file system on your computer, in these little units called znodes. And finally, and this is super cool, clients can set watches on these znodes to get notified instantly if anything changes. So let's zoom in on that znode for a second. It's the fundamental piece of the puzzle. Just think of it like a tiny file or folder. It has a path, like /config/database URL, and it can hold a little bit of data, in this case, the actual database URL. This simple, hierarchical structure turns out to be an incredibly powerful way to organize all that coordination data. Now, this is where it gets really, really clever. Not all Z nodes are the same. You've got persistent Z nodes, which are for things that should stick around, like, say, configuration settings. But the real magic, the secret sauce of ZooKeeper, is the ephemeral Z nodes. These things only exist as long as the client that created them stays connected. If that client crashes or disconnects, poof, the Z node automatically disappears. And this simple but ingenious trick is what makes things like automatic leader election possible. A server creates an ephemeral Z node to say, hey, I'm the leader. If that server dies, the Z node vanishes, and all the other servers instantly get a notification that it's time to pick a new leader. It's just brilliant.
And to make sure everything is absolutely rock solid, every single change, every write to a Z node has to go through the leader. And then it has to be acknowledged by a majority of the servers in the Ensemble. This is called achieving a quorum. It's what guarantees that once a decision is made, it is final and consistent across the entire system, even if a server or two happens to fail.
All right, so we've popped the hood, we've seen how the engine works. Now let's see what this thing can actually do out on the road. What do these massive systems actually use ZooKeeper for in the real world? You'll see it used for a few classic, absolutely critical jobs. Leader election, using those clever ephemeral Z nodes we just talked about. Centralized configuration management, so you only have to update a setting in one place and have it instantly available to thousands of servers. Distributed locks, to make sure two services don't try to write to the same critical resource at the same time. And service discovery, which is basically a live directory of all the available services in your system. It's a direct solution to all those chaotic problems we talked about at the very beginning. Okay, for any of you out there who are developers, listen up. This next part is for you. It's super important to understand the pilot's manual. ZooKeeper is a very specialized tool, and you need to know its flight rules before you take off with it. One of the first things you have to get your head around is the performance difference between reads and writes. Reads are incredibly fast and scalable because any server in the Ensemble, any follower, can answer a read request. But writes are intentionally slower. They have to go through the single leader and get that majority agreement, that quorum. This is a deliberate design choice that prioritizes consistency and safety above all else. And you absolutely have to respect these limitations or you're going to have a bad time. First, ZooKeeper is for small amounts of data. Think kilobytes, not megabytes or gigabytes. Second, and I can't stress this enough, it is not a general-purpose database. Don't try to use it like one. It's for coordination metadata, period. And finally, while it is fault-tolerant, if you lose the majority of your Ensemble servers, the system can no longer process writes. It's in a read-only state until you can get that majority back online. So if there's one single thing you walk away with today, please let it be this. ZooKeeper is designed for coordination. It is not and was never meant to be a replacement for a traditional database. Use it for what it's absolutely brilliant at, being that rock-solid source of truth for your distributed system state, and it will be one of the best tools in your arsenal. ZooKeeper really did lay the foundation for the kind of reliable, massive-scale systems we all depend on today. But as those systems get even bigger and more complex, the challenges of coordination just get harder and harder. And that leaves us with a final thought. What's next? What will the next generation of air traffic control for our digital world even look like?